In this lecture, we're going to revisit our idea of a C++ program memory map. We have seen that the C++ development workflow really goes like this. We have a program typed out in our IDE, we pass that through the compiler, and we get a binary executable, which is a binary representation of the code we have in our C++ program. You can then run that program on an operating system. For example, here I am on Windows. If I double click on my .exe file, for example, our applications are called rooster.exe. You've seen me run this 1,000 times by now. If we double click, this program is going to be loaded in our computer memory. And by memory, I mean random access memory, the memory that is going to be actively running things when they happen in your computer. Is different from the hard drive storage that can also be called memory, and this can throw off a lot of beginners. We are talking about RAM here when we mean memory, random access memory to be exact. If you double click on your program or open it on the terminal like we've been doing, the program is going to be loaded in memory, and it's going to be stored in a special section of memory called program area. And so far we have been thinking that our program is really loaded in real memory on our computer. But that's not the case. It is an idea of the memory that the program thinks it has, but it's not the real thing, and I am going to explain. But before we explain, let me elaborate on the reason why this is done. If we have many programs and each program is going to use real memory on our computer, we could quickly run out of memory because there are many programs. You might even have hundreds or thousands of programs running on your computer. You may never have enough memory to run them all if real memory was used by each program. So the idea was born to create what is called virtual memory. And it is a trick that fools your program into thinking it is the only program running on your operating systems, and it owns all the address space or all the memory on your computer. That's what your program thinks. And the view that your program has of that memory is called a memory map. Each program is abstracted into what we call a process. You can think of rooster.exe that we have been building as a process on the system. And each process has access to the memory range between 0 and 2 to the power of n, where n is the number of bits that your operating system supports. For example, I am on a 64-bit operating system, so the range for my memory is going to be between 0 and 2 to the power of 64, and that's a lot of memory. My program is going to think that it owns all, and it can never run out. It's going to do whatever it wants. If you are on a 32-bit system, that's going to be between 0 and 2 to the power of 32, and that's going to be your virtual memory, the amount of memory that your program thinks that it owns, and it happens to be the entirety of your RAM that you have on your system. Each program basically thinks that it owns the entire memory, and it can do whatever it wants. Okay, so we have the real memory, which is random access memory, and we have virtual memory, which is going to be between 0 and 2 to the power of n. Okay, so now we're going to update on the idea of the program execution model because now we know more. We know about virtual memory. Here is our C++ program. It's going to go through the compiler, and we are going to generate a binary file, which is going to be a representation of how things are going to be laid out in memory in our program. And if we run the program, it is going to go through a section of the CPU called Memory Management Unit, or MMU for short. So that MMU is going to be basically transforming between the memory map of each process and the real memory layout that we have in RAM. What the Memory Management Unit does is really transform between the representation we have in the memory map and the real thing we have in RAM. The entire program is not loaded in real memory by the CPU. Only parts of the program that are really going to be used soon are loaded in memory, and this is going to make effective use of the memory parts that are not likely to be used are going to be discarded from memory and stored on the hard drive instead. And this is really cool. Please note that the real way these things are done is really complicated, but it is buried down into the logic of the CPU and whatever. You don't really need to worry about this as a C++ programmer, but there are a few things you need to know as we are about to see in this lecture. So memory management unit helps out in mapping between the memory map you have in your program, basically the idea that your program has of memory, and the real thing that we have in memory. Okay, here is a slide that is going to drive this home. We have a few programs with their own separate memory maps. We have program 1 through 4. If we execute them, they are going to go through the memory management unit. And the memory management unit is going to assign them sections on the real RAM that we have in our computer. And they are going to be using that section on the real random access memory that we have on our computer. The thing is, your program is going to really think it owns the entire thing. But it's not. It's just going to be using a part of it. And the memory management unit is going to be transforming between the idea that your program has and the real memory that we have on our computer. And the memory map is a standard format that is defined by the operating system. This is why, for example, you can't take an executable that was set up on Windows and directly run it on Linux. This is an operating system thing. The memory map or the structure of your program is defined by the operating system that is going to be running that program. So all program written for an operating system must conform to the memory map that is defined by that operating system. So all programs on Windows, if you had a way to go in and look at the memory map, they are going to be pretty similar. So we have been talking about the memory map, but what does it look like? Well, here is a slide that is going to try and clear that out. So we're going to have a bunch of memory locations from 0 all the way to 2 to the power of n. And the memory map is really divided into a lot of parts. For example, we have the text section, we have the data section, we have the heap, stack, and system. And this is one view you can have on this. There are a few different versions of this slide that you're going to see on the internet. But what is really important is stack and heap for our purposes here. Stack is what is going to store our local variables. Think the A that we have here in main, B, C, things we had inside functions. Those things are stored inside the stack section of our memory map. Besides the stack, we also have the heap, which is going to be the location where we get additional memory we can use to make things better for our program. We also have the text section, which is going to load the actual binary of our program so that the CPU can execute it. But we're not going to worry too much about this section in this course because it is out of scope for what we are trying to do here. We are going to focus on stack and heap because heap is actually going to be very important from the next lecture when we start talking about dynamic memory. Heap is going to be additional memory that you can use in your program if you run out of stack memory. And we're going to see a few other reasons why you might want to use this as we progress in this chapter. So our memory map is going to have a lot of parts, but the parts that we really care about in this course are stack and heap. This is really all we set out to do in this lecture. I hope you have a better idea of the memory map and how this really works. We introduced another view that you can have on how your C++ program is executed, and I hope you have a better idea of the memory system. And we are going to start and see how you can work with dynamic memory allocation, which is going to really use the heap starting in the next lecture. Go ahead and finish up here and meet me there.